and you might want to go back through it. Still in chapter 11. So 11 is all about stress considerations, different stress considerations. So we did Poisson's ratio. We did thermal stresses. The next one is stress concentrations. So if the cross section of a structural piece is altered, you're going to get a stress concentration. Altered can be in this class. Altered can be kind of three interesting ones. Two of them make sense to me, and I have done both of those, but three cases. One case is we put a hole in it. That happens a lot. We have a cross section, we put a hole in it. It's either for something to attach or a bolt to go through or something to hang or a bracket. For some reason, we pop holes in everything. Okay. The other one that's pretty common is the cross section changes. So it goes from a big cross section to a smaller cross section. So those are very common. This one, I don't really know the situation where we put notches in it, but this is the other one they did. So those are the only three cases that we can actually calculate in this class. Kind of beyond that, if it gets trickier, if the cross section goes from a circular shape to an elliptical shape to a polygon shape, like a cam shaft or some kind of shaft, that's beyond our scope. We can calculate average stresses all day long. And average stress is this, right? It's P over A. That's what we've done. So that's given me the stress out here away from the change, right? So we could do that, like if it was a circular section, we could do P over A and get the average stress. And then if that changed to an elliptical shape, we could do the elliptical shape, P over A. And if that changed to a polygon, we could then do the polygon. But those transitions are going to have stress risers. And we just can't do it yet. Beyond the scope of this class is what the book says. So we'll do these two. And this one, you'll kind of get the drift of how it works. You'll be able to do this one too. But the hole is pretty common. And just to review a little, P over A is average stress. It's away from where the load's applied, and it's away from any deformity or any alteration to the cross section. So P over A is the same thing we've always done. Load 4,000 pounds over area 0.1 times 2 inches. So I'm going to do that one first just to see if we're anywhere near, we'll call this steel. A36. See if we're anywhere near the yield. So this is 20,000 PSI. A36 yields at 36,000. We're good, right? So the average stress, this stress right in here, this is tensile stress average, away from kind of everything, right? It's 20,000. At least that's what I get. I'll do it again. 0.1 thick times 2 divide. Yeah, 20,000. Okay. So then the next thing, when you see this kind of thing, we're going to need to know the stress next to this hole. So they draw some stress curves in the book. It's kind of interesting. And it is how it works and how it looks. Like if you were to do a SolidWorks element analysis of something that had a hole in it, it would do this kind of graph for you. It uses colors, not lines, but it would make it red, like around the hole would be red because That's the magnitude of the stress. That's how they're drawing this curve. So out here, it's about average stress, right? But next to the hole, it's a stress riser. It's a concentration of stress next to the hole. So
would that be mirrored on the other side of the hole too? All around it?
yeah, you draw one, it's like a graph. So you draw it one direction, but yes.
Okay.
Yeah. So the way SolidWorks would do it is not just here, right? It would be all the way around the hole would be super red, and then it would get lighter red, until out here, it would get close to average stress. Right? Makes sense. If you've seen any hole that's been loaded or overloaded in a structural member, it'll have little cracks coming off of it. That's just the beginning of a failure, right? And that's because those cracks are going to start right in here. And that's because of that stress concentration. So same with these other changes, right? The stress riser is right next to the change. All right, so how do we calculate it? We use a new formula. It looks very similar. It is K P over area net. So it's still P over A, but we put in this K factor. And that's kind of the challenge, is to find the K factor, right? The rest is pretty simple. Area net is the leftover area. So where P over A, we use the entire cross section, right? For P over A, for the average. Area net means, okay, there's a certain amount of material removed, right? Where the hole is. We're just going to use this area, the area left over. So it's going to be a reduction in area that will drive up the stress. And then the K factor will drive up the stress.
So if you were looking at the cross section, you wouldn't see the circle, you just see.
Yeah, so if we, exactly. So here's the cross section for average, the cross section for the concentration would be that, right? The hole's removed. So really you just like pull out that. You pull out this dimension when you calculate the area. So instead of the full length, it's going to be 2, take away 0.25. This and this are going to add up to 1.75 times the thickness, right? Does that make sense? So area net, A net equals 0.1, it's still 0.1 thick, but now it's not the full 2, it's 2 minus, oh, that's a radius. So it's 2 minus a half. So it's 1.5 inches. Right, because I had an R next to it for radius. So it's a 1/2 inch diameter. Take a half away from the 2, you get 1.5. Still 0.1 thick, so that's area net. P is still P. 4,000 pounds. Right? And now we need this K factor. So to get K, there's a graph. Anytime there's a graph, that means it is subject to our interpretation. So we'll end up with some slightly different answers typically. It is a stress concentration factor for flat bars. So they call out flat bars, and we're going to do 3 cases. One is circular hole. That's the one we're doing. That's this graph. Semicircular grooves. That's this creature. And then fillets. That's this creature. So you match the graph to what you have. We have a hole, so we're dealing with this upper line. Okay. Here's the K factor. And here is the R to D ratio. So R is different, not really different, but it's a little different for each case. And it's identified within each little diagram. So circular hole is 2R. It's clearly the radius of the hole is what R is. Okay. And then D, it's little d, And that is the leftover material. So this is 1/2 D and this is 1/2 D. Just think of it's the leftover material length. Okay, so in our case, we have an R of 0.25. I don't even know if this is for what I'm doing, but that makes sense. And then we have a D of not 2.5, but we have a D of, right? It's from here to here because this is 1/2 D. This is, thank you. So this is 1/2 D and this is 1/2 D. So it's this leftover distance is what it is. So it's 2 minus the 1/2 inch. It's 1.5 inches for D. So D equals 1.5 inches, R equals 0.25 inches, and my R to D ratio would be 0.166. It's unitless. R to D ratio of 0.166. So there's 0.15. So 1.6 is going to be in here somewhere, right? And that's about as well as you can read the graph. 0.166 in here, and then you follow it all the way up, and you land on whatever change you have. We have circular holes, so it's right here. Looks like it's just below 2.4. Yeah. Like I said, we're all going to get something a little different. Some will read it as 2.4 and they'll just be done. Others will say, oh no, it's just a little below 2.39, you know.
Is there a way you want to lean for safety? Like,
Not really. Not really. Your factor of safety is gonna deal with that kind of thing. So yeah. So we'll say 2.39. So our K factor is 2.39. And again, it's just a multiplier. So it doesn't have a unit. But it goes here, right? It's a multiplier to this P over A times K. So then our stress max is going to equal, and I'll just write it all the way out, 4,000 pounds divided by our area net, which is 0.1 times 1.5. I didn't leave room for my K, so I want room for the K. And my K is 2.39. What do you get? Yeah, 63,733 PSI. What do you think of that?
So that's compared to the stress in the area with alcohol.
So average stress out here, we calculated at what, 20,000? Right? Yeah, so that's out here. And what's our yield? 36,000. So we're good on the average stress out here. And then what's our stress concentration? 63,000. That's really bad idea. So yeah, the stress concentration right next to the hole is giant. there's definitely gonna be permanent yielding and some kind of cracking going on and not a good thing. No, no good. Okay, it's big, like stress concentrations are really driven up. So you have to account for them, for sure.
See a lot of like, in like, innovative stuff.
Yep,
uh,
lightning holes, yeah, yeah. Yep.
So that significantly affects the.
It does significantly affect it, yep. Yep. Now, the ratio is important. So this is a 1/2 inch hole in a 2-inch wide piece of material. Removing quite a bit of hole. I mean, that's quite a bit of material coming out. It's a big hole compared to the piece, right? If we change it to, you know, a smaller hole, we do the calculations, we probably get a different number. Because it's really driven up by K, and that's that R to D ratio. So this R to D ratio, the lower that is, the more trouble it is. So yeah, you just got to check it. Just got to check it. All right. Very good. It's that process over and over, and we only have the 3 shapes. So what you have to be careful with is just making sure you understand these little diagrams, because that's how you determine R and D. So they're pretty easy, I think. D here, right, is just the distance. It's the material that's left after the reduction. Same thing over and over. So that's what D is. And R is typically the radius and the radius. So it's pretty simple to do. It's not 2 times, right? Even though there's a radius here and a radius here, it's just R. So there's got to be a lot of things just right for us to calculate it. Like these 2 fillets have to be the same. They can't be different radiuses.
Is there
Or it changes the game.
like a fairly concentrated graph in a specific area?
Yeah.
So if we do this kind of thing out in like the real world.
Yep.
Assuming you have is there a resource that you use that has like a larger group?
There isn't, not really.
Okay.
It's
So if you
probably,
need to find K for like
yeah, somebody's probably gonna run an FEA analysis on it if it's gonna have all kinds of strange.
my pay grade, I think.
Yeah, well, a finite element analysis somehow. So nowadays that's via software. So you're gonna put the design in a software, you're gonna load it, and it's gonna run an FEA out and give you
Is that
stress.
gonna be for most things? Kind of
Quite a
software?
bit,
Yeah.
like the things that we don't are not doing that for is construction. So, you know, I mean, there are truss softwares that will run the truss calcs for you. But beyond that, like beams in a home or a commercial building, those are all done by hand still. Lots of that stuff is done by hand. And we pop holes in all of that, right? The electrician's gonna drill holes in absolutely everything. And then the plumber's gonna come through and he's gonna drill giant assholes and stuff. So, yeah, well, that's where it's like, this is super common. But like in machine parts, automotive parts, those kind of things, the software driven FEA analysis type of thing. The thing is, you don't always, it seems like you don't always get great data out of a software. Sometimes if just inputs are wrong, you know, you're supposed to put in PSI here and somebody puts in KSI, or the other way around. Supposed to put in KSI and someone puts in PSI. It's got to be square inches, not square feet, or, you know, so you got to have some feel for it. Like just doing P over A on this gives you some feel for like, okay, you know, this can handle it, no problem. I wonder what's going on here type of thing. So this kind of is kind of fun because in SolidWorks, you can set that up and then you can run the analysis and you can get the stress risers and see if it's close type of thing. And it's pretty close, as long as you get the material the same. Good. That's pretty straightforward. I'm not gonna give you any twists or curves. You have a couple of those to do for homework. And then I'm jumping forward, man, and getting into shear and moment diagrams. So I'm gonna do that too today. Because then on Thursday, you'll have some homework in that. And this is kind of it's meat and potatoes, like we've got to get to it and really be able to do it well. So This, like, I don't know, what, will you ever do that? I don't know. It's hard to tell. But it's pretty simple. At least you know it exists. You'll do some homework in it. But beam analysis, hopefully you do, because it's super fun. So this is going to go back to statics in chapter 13. So we're skipping chapter 12, it's torsion. It might come back and pick it up. But again, torsion could be like a stress consideration, right? It's just a twisting stress. So we could lump it in or just cruise by it because it's super mechanical, machine design type of calculation. So I might come back to torsion, but it's really not part of beam analysis, and I definitely want to get to beam analysis. So the first part of beam analysis is statics. So I just want to go back through that because you'll have to do statics in some of these. So I've given us a beam with a roller and a pin, a distributed load. So stack of plywood or concrete or something it's been stacked on here. Or this is where, there's an appliance collection, like a kitchen has a larger distributed load than the rest of the home type of thing. It could be tile floor, it could be cement floor these days, could be heat in floor creates a distributed load. So many different things. So we'll have to remember how to deal with that in our statics. And I did 0.2 kips per foot on the distribution and 1.5 kips out here. So first thing we got to do is free body diagram. We've got to learn what the reactions are. Our goal is to maybe size this thing. That's what I'm going to say. So what size? And we'll call it Doug fir because we use a lot of Doug fir. So it's going to be wood. This could be a porch. This could be, an interior wall. So those supports can be all different things. What do we do first? Yeah, love it. Yeah, get the reactions in. How many for a roller? A roller. And what do you think? Up or down? Yeah, pretty sure that one goes up. And then the pin is 2. What do you think? Up or down? I'm going to go with up, but this is a big load out here trying to flip it, right? So we could be wrong on that. And then there is an X, but there's no X load, so that's just 0. So that's good. Free body diagram, done. Now what? Oh, it's been a hot minute since we did this. Yeah, we want to concentrate the distributed. So for statics, we concentrate the distributed. For strengths, we want the distribution back, but we have to concentrate it for the statics part. So how did we concentrate a distribution? We calculate the area of the distribution. So whatever the distribution looks like, if it's a triangle, we do the area of the triangle. If it's a rectangle, we do the area of the rectangle. If it's a trapezoid, we do the area of the trapezoid. Okay. So the area of this rectangle is 10 feet times this is the height. So when they give you this, it's always the height of the distribution. So it's 10 times 0.2. Which is what? 2. And where do we put it? Through the geometric center. So if it's a rectangle, it's just halfway. If it's a triangle, you got to look that up if you don't know it. 1/3 the base, 2/3 the base, whatever it is. So through the geometric center, we put the concentrated load 2K. Again, it's just for statics. Once we get done with statics, in other words, once we find these, then we're gonna just ignore this 2K. It's gonna go back to its distribution. Okay. All right, now how do we get these? Yep, sum a moment. Summing forces is not gonna help us. There's two unknowns. We gotta do a moment. Let's do the moment at where? A. Why at A? Because we need one of those to drop out. You could do it at B, that'd be fine. B would drop out, but if we do the moment here, AY drops out, and we need that to happen. So it's going to be 2K times 5 feet, and the rotation is negative. Clockwise negative, yep. And then we have BY. I'm just going to work my way across the beam. BY times 10 feet. And its rotation is positive, counterclockwise. And then 1.5 K times 15 feet. And its rotation is negative. And all that we said equal to 0. And we solve for BY. Anyone else get 3.25? Oh, good. Came out positive? Yep. So that means what? Yep. Direction's good. It is definitely up. Yeah, so leave this, if it's positive, leave this alone. Don't move it. Yeah, so leave this alone. If this is positive, leave it alone. Take this, move it to the other side, and that makes it positive. Take this, move it to the other side, that makes it positive. Those are just numbers, add them together, and then divide by the 10. That was a lot, but you get it? Okay. And then how do we get AY? Yep. So what do we got coming down? 3.5 coming down. Yeah. And then we got 3.25 going up. So we must need another 2.5 going up. Is that right? Yeah. So it's kind of imbalanced, not completely imbalanced, but a little close to imbalance. AY is not very loaded. Almost flipping over, but it's not. So we did this, we got this by doing some forces in the Y. And that would be -2 minus 1.5 plus 3.25 plus AY equals 0. That would be the equation. And then again, just leave AY alone. If it's positive, just leave it right here. This moves over, this moves over, this moves over. And you end up with a 0.25. Cool. All right, so now we're done with the statics. Statics is done. We have all the forces we need. The 2K goes away. We're back to the 0.2K per foot. And we have to progress. So when we're doing beam design, this is kind of beam design, a little bit beam analysis. It's analysis if you know everything. You're just analyzing the situation, right? If we knew the load and we knew this was a 4x6 Doug fir, then that's just analyze it, right? So if you don't know it's 4x6, then it's a little bit designed like, oh, we have to figure out how big to make this thing, right? So what we need to know is we need to know what we're going to use, and we're going to use shear stress, which is 1.5 V over A. That's the equation for shear stress for a rectangular beam. Try to draw a little rectangle there because it's very specific to the shape. Now, shear stress is like, right? It's just shearing it off, not bending it, just shearing it. It would happen like next to this support. Like if this beam literally just went sheared down, so much load, they just sheared it off, right? That's what this is checking. So the two things that we want to think about is shear and bending, which we've talked a lot about. Which is MC over I. Okay. So the two things you need is you need V, which is shear force, and you need M, which is bending moment. We know what moment is. It's force times distance. We get that. V is just a force, a shearing force. So shear setup is this, where you have V up and V down, and they're very close to each other. Okay. So for example, we have BY, which is 3.25 up. And if this thing's in equilibrium, there must be very close to it. There must be a 3.25 coming down. So if that was true, 3,500 pounds and 3,500 pounds, is that enough to shear off whatever size this is? That's what we're trying to like figure out. Rarely is that the case. In other words, shear is not typically the control. It's normally fine. Beams handle shear, no problem. What the control is this bending stress problem. So we think about this first and we would make our choice. Like if this was what size, we would make our choice based on this, and then we would check this after we choose, because then we'd know the area, right? And we just calculate it. So that's kind of the flow. The two things you need though is you need V, shear force. What's the greatest shear force? I don't have any idea, right? And I need M. What's the greatest moment in this beam? I have no idea. So the way we get that are the shear and moment diagrams. We draw diagrams. It's kind of trippy, but it's super fun. And you'll see, I brought in the calcs. I can show you some shear and moment diagram, but this is what we all do. Like we draw a graph of the shear force. So I'm going to draw a straight line that represents the length of the beam. And it is the V, I like the purple, V equals 0 line. So that's shear equals 0. So it's a graph that's going to go up and down, but the horizontal line is 0. Okay. And this is the same length as your beam. So since V is a shear force, it's not a moment, it's a force. We use the existing forces to draw the diagram. Okay, we literally, I always say we follow the forces, just do what the forces do and you'll be fine. So you start at the left side and right at the very end, just past this AY force, we see the AY force. Right? And how big is it? 0.25. And which way is it pointing? Up. So my graph at the very end, I go up 0.25. Now I've kind of ignored the distribution because I'm like infinitely close to the end of the beam. And where the distribution doesn't show up yet, the distribution needs a length to show up. So I'm right at the end of the beam. I just get past this and it shows up. And now as I move along, the distribution is going to start to show up. Okay, and which way is the distribution? Up or down? Down. So it's going to, from this point, it's going to drive the graph down. How much down? Per foot. 0.2 per foot, right? So we're up 0.25. In 1 foot, we are where? Down 0.2. Right? And then at 2 foot, we're down 0.4. Right? So here's 1 foot of beam. We drop 0.2. So that spot right there is 0.05. Agreed? I mean, it's above the line still. But then we go down another 0.2. For every foot, we're going to go down 0.2. Yeah? So since this is horizontal, the graph in the shear diagram will be a slope, straight line, but slope. Because it's linear, right? It's dropping 0.2, 0.2, 0.2, 0.2. How much does it drop in its full length? 10 times 0.2 drops 2K, right? So it goes from 0.25 down here. Oh, I should be over in line with this. Okay, down here. So it's not negative 0.2 because it started at 0.25, right? So it's negative what? Yeah, 1.75. And it's definitely a straight line. Meaning that it's falling the same amount all the way through. And it's going down because the graph, the load graph is pointing down. Make sense? So distributions are a little tricky if they're horizontal horizontal loads like this, which is a uniform load, then it is going to be a linear graph. Okay. All right. Then what happens? I get to the end of the distribution and I just go past BY and BY shows up. How much is BY? 3.25. Which way? Up. So it's going to go up 3.25 from the 175 negative. I get 1.5. Is that true? I'm going to change my 3.25 enter 1.75 minus 1.5. I'm going to make my graph a little more accurate, so I'm putting it here. Yeah. And then in this region, force-wise, what happens? Nothing. There's no forces. Nothing changes. There's no distribution. There's no concentration. So it just stays. So if nothing happens, it just stays horizontal. And then the shear diagram always returns to 0 if you've done it right. Right? Because 1.5K drives it down. That is your first shear diagram. And that's kind of a complicated one because it had a distribution in it. Like if there's no distribution, it's just like, you know, it's a bunch of straight vertical lines and horizontal lines.
So the shear happens at that.
So yeah, that's what we want to know is like the thing we need to know for this is what's the maximum shear? The maximum shear is just the greatest value on the graph. Not the combination of values, but the largest value. Doesn't matter if it's plus or minus. So what's the largest value on the graph? Yep, Vmax equals 1.75.
Does it
Okay,
equal negative 1.75
Nope.
or just?
just absolute value. The negative is important for the moment diagram because we build the moment diagram from the shear diagram. So that's just the shear diagram. And I said, hey, we need shear and moment diagrams, right? Because that's V. So now we could do some kind of shear analysis because we know V, we could maybe work on getting A, right? But this is not typically the control. We need M, the maximum moment. All right. So that means we just get to do another diagram, the moment diagram. I'm going to tuck it in a little bit close. It might go a little bit on top of the, it shouldn't. M equals 0. All right. So here's the deal. The moment diagram, we can develop the moment diagram from the shear diagram. There's ways to do that. But you can also literally just go plot points. We know what a moment is, right? It's force times distance. So if I needed to know the moment at the very end, and if it's not fixed, in other words, if this is a pin, that means it's free to rotate. Moment is rotation. If this is a free end, nothing holding it there, then both those ends are free to rotate. And we do beams that way. We want them to rotate. It's less stress. If you fix them, like encase them, and then you load it and it wants to bend and rotate and it can't, it's developing extra stresses that we don't want. So at the ends of your moment diagram, you're going to be 0, right? So I know it's going to start here and it's going to end here at these free ends. The only time that's not true is if you have a cantilever, right? Something built into the wall and you put a load on it. That's a cantilever, big moment right there, right? So that's not a free end. That's a encased end or something. Telephone pole. The end is not free. Like that's what's holding the whole thing up, right? Giant moment down at the bottom. All right. But this beam, what we call simple beams, we like them to rotate. That's a good thing. All right. So I'm going to show you plotting first, because that's something that we can always do. If you're not sure what the graph does, plot points. Okay. So that means go over at 1 foot and calculate a moment. So if we do that, go over here at 1 foot, draw a line through it. You can look to the left or right. To the right looks a lot more complicated. To the right looks a lot more complicated. To the left looks pretty simple. And you literally draw a little section of the beam that's 1 foot. It has a little distribution on it, and it has a AY of 0.25. And what you want to know is the moment at that little section. Oh, it's kind of on top of it, isn't it? So here's my little drawing. Here's my distribution. That is 0.2 kip per foot, right? So you have to do this little moment, and the spot you're doing the moment is right here at 1 foot. So we concentrate it because it's a distribution. So that the concentrated distribution is 0.2 times a foot, which is 0.2. Yep. Okay. And it's times a half a foot for that one. And this one, it's times a full foot. And you just have to calculate that number, this little moment on our little section of the beam, right? So what's it going to be? It'll be the 0.25 is going clockwise. So it's negative 0.25 times 1 foot. And then this one is 2K 0.2, right? Times 0.5, and it's positive. And that's going to equal the moment at 1 foot. Kind of a little drawing, I know, but. So we've taken 1 foot of the beam. And we've looked left and drew this. So this is the distribution. This is the reaction. So I'm right here at 1 foot. Okay. So how much is that? 0.2 times 1 is a negative 0.25. Right? Negative 0.25 times 1. And then 0.2 times 0.5. That is 0.1, but it's plus, so I'm going to do that. And I end up with a negative 0.15 foot-pound. Negative meaning negative, this is positive, this is minus. So I'm going to exaggerate it a little and put it right there. Yep. It's negative, right? It's at 1 foot. And it is 0.15 foot-pounds. I might calculate it again. Oh, it's actually, yeah. So we calculated M equals negative 0.15, correct? You guys getting that? Here's a blow up of it. Here's our beam, our 1 foot, our distribution, 0.2 kips per foot, right? And 0.25 kips. I got all those numbers right? 0.2 and 0.25, yeah. And this is our 1 foot section. Yeah. So then we concentrated this and said, okay, that's 0.2, okay. And it's times a half a foot. So the moment is going to be 0.2 K times my half a foot. And that one is positive. And then this one is 0.25 K times 1 foot, and it's negative. So we ended up with a negative point. Correct? Yep. Everyone good with that? This is the moment out here created by that force and that force, right? That's what we did. The internal moment. So the moment out here is a clockwise moment, 1.15. Right? Adding these up, this is what we get. The internal resistance is opposite of that. So it's plus. So I made a mistake when I put it down below, because this is the moment here. It fights the moment you calculate. All right, so this one should be, really should be positive right there. Sorry about that. I knew I was wrong. I'll show you why. 0.15 kip feet. Because we want that internal moment. We want this one. The one that's fighting the external moment that we calculate. So the internal is positive, fighting the external, which was negative. All right. So it's actually up. So the way I knew I was wrong was the shear diagram is telling me slope of the moment. So you can get the slope of the moment. This is kind of trippy. If you've had calculus, you'll like it, but if you haven't had it yet, then you won't quite, maybe you won't love it. But if the shear is positive, see how it's positive here in this little triangle? Then the slope of the moment is positive in the same region, meaning that positive is the slope is up and to the right. That's positive, right? So this is telling me the slope of the moment is kind of like this. I'm going to exaggerate it, which is going to put my mark in the wrong spot, but that's all right. So here it's positive, and then it's less positive and less positive and less positive until the slope is 0. So positive, less positive, less positive, slope is 0. Trippy, I know. This is telling me slope of this. So that means this slope here is what? Negative, negative, getting more negative until it's really big negative, right? So it's going to go negative, and then it's going to come down to this, which is really negative, meaning downhill, right? Really negative here, just barely negative there, creates this kind of thing. So if you can read the shear diagram plus and minus, you're getting the slope of the moment diagram. So here it goes to what? Positive. So this goes positive. And then it stays the exact same slope positive. Exact same slope means straight line. Trippy. Moment diagram though. Wow, that's cool. So the strategy is to be able to draw it. If you can draw it, then we don't have to plot points. Like, I don't need to know what's going on 1 foot. I don't even need to know what's going on at 2 foot or wherever the hell this is, because it doesn't even look close to that value. And all I want is maximum moment. I want to know where's the biggest moment, what is it, right? So that's this point. M max. If this was even close, I'd calculate it so I could tell which one was bigger, right? But this looks like clearly this is a tiny little area. This is a big area. This is a big moment. So right here is where I need to know the moment, and then I can plug it in to there. So 2 ways you can get the moment at this point. You can go just up to the beam and calculate it, right? Just like we did the little 1 foot section. We can go up and say, oh, I'll just go right here and look to my left and calculate the moment. That works. That always works. The other way you can do it is by the area of the shear. It'll give you the moment. So this triangle is a positive area. This triangle is a negative area. You got to add them up, because if you want the moment here, you got to look entirely left or look entirely right. I'm like, oh, well, this is way easier right here. This is just a rectangle. How do we get the area of a rectangle? Piece of cake, 1.5 times 5 feet. $7.5. Right? Height is 1.5. Base is 5 feet. The moment here, 7.5 kip feet. That's a lot. I'm gonna stop there. We never got to how big the beam is. But you won't have to do that in your homework, so. All right, that's a good first hit at it. These are super fun to do. And that's how we determine if beams are good or not. It's how we design. We have to be able to draw those diagrams, which means we have to be able to do the statics without error. That's a problem. But good job. Your homework's in stress concentrations, but you could look forward to Thursdays and you could work on that one too.